It's important to practice solving physics problems the right way. For many problems, this involves starting with a free body diagram. A free body diagram establishes a conceptual representation of a body and all the forces acting on that body, and can be referred to when writing equations, such as the sum of the forces in the x and y directions. Consider the following situation, where a man is trying to pull a crate with a rope across a rough surface. Here, let's consider the case where he isn't pulling with enough force to move the crate, so the crate remains stationary. In physics, the object, here the crate, is reduced to a point. We will leave in a silhouette of the crate and its surroundings for reference. Now we will include the forces acting on the crate. First, the applied force, F, then the force due to gravity, Fg, the normal force associated with the surface that the crate rests on, and the force associated with static friction, denoted Fs. You may have noticed that the forces are not all drawn to be the same length. While there is flexibility with the lengths of the forces, there are some rules associated with the relationship between these vector lengths in your diagrams. In this problem, the crate isn't moving in either the x or y direction. Conceptually, the way that we draw our free body diagram should communicate that. While you won't draw the vector components in your free body diagram, it's helpful to visualize them. Here, there are three forces acting in only the x or y directions. The force F, however, has components in both directions. Since the crate is not moving in the x direction, the forces applied should roughly cancel. These are the forces Fs and the x component of the force F. You can see how the x component of F and f of s are approximately the same length. If we added these vectors together, they would cancel each other out, roughly equaling 0. The block is also not moving in the y direction. There are three forces to consider here: the normal force, Fn, the force due to gravity, Fg, and the y component of the applied force F. The forces acting in the upward direction, the positive y, need to be balanced by the forces acting downward. So in this case, the force due to gravity needs to be balanced by both Fn and Fy. Adding Fy and Fn together in the positive y direction results in a force vector approximately the same length as Fg in the negative. The diagram that we are looking at is well balanced. When you draw your diagrams in ExpertTA, they don't have to be perfectly balanced, they just have to be balanced enough that they don't miscommunicate the physical situation. If you were to draw Fs a little shorter, like this for example, the diagram could still be considered correct. If you were to draw Fs much shorter, as shown here, the physical situation is not accurately described. Here it looks like there's a much larger force to the right than to the left. The diagram shown here communicates that the crate should be moving to the right. The ExpertTA system has a way to help you know if your free body diagrams are balanced. Let's look at the same crate problem in this system. Notice the x and y axes indicators on your screen. These will help you determine if the forces are roughly balanced in both directions. You can see here there's a negative x-axis bias, indicating acceleration to the left. To adjust this, we'll reduce the magnitude of the static friction force. Notice now, the indicator lets us know we are in equilibrium in the x direction. Reducing the magnitude too much produces an out-of-balance diagram with a positive x-axis bias, indicating acceleration to the right. Here you can see the feedback provided when Fs is much shorter, letting us know that the forces in the x direction should cancel out, roughly equaling 0. Referring to axis indicators can help you determine the correct magnitude range for your force vectors. You can see that the accepted diagram and the correct diagram are not exactly the same. There are multiple right answers depending on the proportionality of the vectors in your diagram. Keep in mind that some diagrams may require you to indicate that an object is accelerating in a certain direction, in which case you will want to draw the diagram with an axis bias in the direction of acceleration. Select Add Force to populate the diagram with vectors. Drag and drop them into the appropriate position and make sure the labels match using the menu on the right. For this example, the ball is dropped from a tall building and is accelerating downward in the negative y direction. Reducing the magnitude of the drag force in our free body diagram will illustrate this concept appropriately. Notice now, the y-axis indicator lets us know there is a negative bias, indicating that the ball is accelerating downward. If you have any questions related to free body diagrams, please contact main@theexpertta.com.